Yeah.
I never got my homework paper, so I
Oh.
can never find it.
I might have some there. Yeah, I might have misplaced it. I can look for homeworks and see where it is. Okay, I'm not sure.
I never get other one.
Well, that's good.
So,
Okay, okay. I don't know. Yeah, I don't know what the deal is there. I'm sorry. Yeah, well, maybe we have them. There's coming around today. There's 2 folders of them today.
okay. I think I already looked in that folder.
Oh, there's 2 folders today, but
Okay.
and there's others sitting around. Yeah, I should do something like, I don't know how to do that exactly. Well, it's nice to see your own, though it's good to have your own homework in addition to what the solutions, because you remember what you did. I mean, that's desirable. I appreciate that's a good point. I think that's totally reasonable to have your own stuff. Of course, you don't want to memorize. You don't do it wrong and then not realize it, memorize it, but get it totally fixed in your mind how to do it wrong. But anyway, no, your own stuff. You probably figured it out, and then when you see it again, it'll remind you very effectively. So let's see. So how can I do that? I think what I'll do. Why don't I do this? This is the faculty lounge. There's faculty mailboxes there, and then there's a space on top. I'll just put up all the homework I can find. Then it doesn't guarantee anything, but I'll look for it. So I'll put this in a stack there, and you can look for it, whatever's there, including, I guess, exams, everything that's old stuff there. And then if people don't want it, there's a trash can nearby. Okay, so there's homework coming back, and then exam, last year's exam. I think the last time I did this, I demonstrated that the tests are too hard by getting through about 2 problems. I think I had a review. The last time I did a review, I got through about 2 out of 5 problems in the class time. It might be like that. Of course, the problem is that if I blast, I could probably do them all in such time, but the communication level of what I'm doing would be low, probably. So, at any rate, the goal today is to go through last year's exam, and the inference is that this year's exam is going to sort of be like last year's exam. So it's not a waste of time. I think that's a rough indication of how long it'll be and the kind of topics and so forth. So that's yeah. It'll be 3 hours.
And how many pages of...
And so let's think about it again. It's open book. It's cumulative, but chapters 4 to 7 and 10. So we have chapter 4, 5, 6, 7, 10, the first part, second part, and last part. And 3 and 2 and 1 is covered only in that they'll be asked maybe conditional probabilities or something that uses that, but really this stuff. So it's not really probability, but everything else. And you can count on probably 1 each of these, just like this thing. And something, at least 1, this could be 1 of each of these, right? But it should be at least, of these 5 chapters, it should be at least 4 of them, would be covered somehow. And probably these, something there. And the idea, okay, let's see. So the homeworks also indicate, so it's open book, but only Ross, and then plus 3 pages. Now the idea here is the simple, if you wanted to, you could bring the first 2 pages you used for the first 2 exams and one more. That's sort of like if you know your page already and you've got it, then you that may be efficient. So that's sort of the thought, if you don't want to waste time. That was the, not that you needed to put lots of stuff on the paper, but okay, and it's going to be 9 to 12 a week from today in 303, where we've been all the time. Okay, so let's see. So I'm going to return all the old homework and exams and stuff I have on top of the mailbox in 319 Mud. So I'll put a stack of stuff there if that some of you are missing stuff. I'll look for what I can find. And there's 2 folders of homework coming back now. And there's coming, so more important is there's a copy of last year's exam coming around that we're going to talk about now. So that would maybe be helpful if you're forgetting. The solutions are online as well, so I didn't hand them all out now, so that this is all there. So there's no point in you don't need to take any notes other than what you shouldn't need to. What's written, the solution should be enough, so it's maybe just paying attention. Okay. Okay. So, let's, here we are. We have the terrific Toledo taxi problem to start with. Some of you, at least one of you, knows the protagonist here, right? Alberto Lopez Toledo. He operates a taxi that provides service in 2 zones of the city, Toledo. Fares picked up in Zone A will have destinations in Zone A with probability 0.6. And sort of city, and there's some regions, A and B. And the fares picked up in A will go back to A. They'll be in here somewhere with probability 0.6, and they'll go over to B somewhere with probability 0.4. And fares picked up in B will have a destination in A. Let's see. Fares picked up in A will have destinations in A, 6. Fares picked up in B will have destinations in A with 0.3 and back to B with 0.7. Then we start asking a bunch of questions. Like, starting in A, what is the probability that Alberto's taxi will be again in Zone A after 2 trips, and so forth. So let's do that. Starting in A, what is the probability that Alberto's taxi will again be in Zone A after 2 trips? So we're starting in A. We could go to A or B, and from A we could go to A or B. So we have this tree, and from A to A is 0.6, A to B is 0.4, A to A is 0.6, A to B is 0.4, B to A is 0.3, and B to B is 0.7. There's a tendency to stay in the same place, sort of vaguely realistic. Then we multiply to get the final probabilities. We get 0.36, 0.24, 0.12, 0.28. We add 0.4, 0.6, yes, so they add up. Then the probability of being in A, the probability of being in A after two moves is equal to 0.36 plus 0.12 because we add these two probabilities. Now, suppose that Alberto, well, so the other part of this problem is we get to see what's the long-run proportion of time that he's in A, if he does this many times. So when we get to there, we're going to want to make this a Markov chain. And then we have A to A is 0.6, A to B is 0.4, B to A is 0.3, B to B is 0.7. Then what we just did was P squared, where we want A, B, and we want starting this entry of p squared. So if we thought about it in terms of the transition matrix, we'd have done this, and that would have just computed these things. We'd have done the same thing. Now, B, suppose that Alberto is in zone A. Suppose that Alberto starts in zone A and is again in zone A after 2 trips. What is the probability that he never left zone A? So it's probability that he went from A to A to A, given that he went from A to A to A, or A to B to A. Because this is from A to A into A to A in two moves. So that's just A to A to A is this one over the sum of these two, right? So this is standard conditional probability. That's this over this. So if we call this C and D, that's the probability of C and D over probability of D, definition of conditional probability. But this intersection is just this, so this is probability A to A to A, that's this. And this D is the probability A to A to A plus the probability A to B to A. And so this was that 0.36 over 0.36 plus 0.12. Okay. So C, what's the long run proportion of time being in A? And so now we have this is hopefully such a problem. The first 2 problems here hopefully get you off on a great start. This is sort of, you think, there's no problems here. You're sailing along. So you want pi A, where you have pi equals pi p, and that's this. So you have pi A, pi b, 0.6, 0.4, 0.3, 0.7. You have to remember to multiply boom, 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 boom. So you're going to get pi A times 0.6 plus, and then this is maybe made easier by made 1 minus pi A, because there's only these 2 variables. So then this is 0.3 times 1 minus pi A, and that should equal pi A. We would get 2 equations and 2 unknowns plus an extra equation here, but we stick rid of this and we get 1 equation. So we just get this, and we get pi A times 0.3, so we get 0.3 equals pi A 0.7 pi A equals 3/7. Probably okay. Okay, D. Alberto's expected profit for a trip entirely in zone A is $6. So we get a $6, A B is $8, B is $8, and wait, let's see. AA is $6. BB is $8, and AB in either direction is 12. Sort of reasonable. Within A, $6. Within B, $8. If he has to go further from one zone to the other, crosses the zone, it's 12. So this is sort of the part of such a problem that would be a little bit challenging. You just make some room here. Here, what you want to do is you've got to cost this out. So you want to say what are the probabilities of these trips? And that's pi A, PAA is the probability of this. And then pi A, PAB, and pi B, PBA, and then pi B, PBB. These are the 4 cases that you're in A and go to A, in A and go to B, in B and go to A, and in B and go to B. So you're actually not, you're being paid per trip, not from where you are. So actually there's two places you can be. You can be in A or B, but there are 4 trips, A to B, A to A, B to A, B to B, and this is the stationary probabilities of the trips. So you want to just think, right? Once you've got this answer, you just see that this is the probability of making a trip from A to A. In the long run, this is the probability of being in A, and this is the probability of going next to A. So this is the probability, the long-run proportion of trips that are from A to A. The long-run proportion of trips that are from A to B, B to A, B to B. And then you're going to multiply by 6. These are both going to give you 12, and this is going to give you 8. And then this thing means you're going to, this 6, you've got to plug in the 3/7 and the 4/7 and the 4 entries of this matrix, right? So and both for doing the problem, this would be reasonable to write this down like this and stop. In other words, that don't make your time. The arithmetic is not critical, but the indicating. So putting the number down is less important. Is not going to give you credit, but putting the right equation down where you've reduced it to just all this stuff is here. This is here. This is these entries, and this is here. So if you've written this down, everything so far, you could write this. Well, you'd have to plus, plus, plus. That would be Alberto's long-run average profit per trip would be this. Which, yeah, okay. Okay, let's move on to the barber shop. In this instance, there is nothing tricky. Just like the book, you see barbershop, and then you think continuous time Markov chain and in birth-death process. So that's right. You could read the thing through a little more carefully than that to make sure you're doing the right thing, because you could make some different problem with barbershop. But anyway, this is consistent with that. So in this barbershop, we have one barber. Christos is the barber. He can serve one customer at a time. He has room for 2 customers. He serves ouzo to waiting customers. It's a nice barber shop, and yet even though he serves ouzo, the customers are impatient, and if they have to wait too long, they're going to leave, even with the ouzo. Okay, right? So it's a strange situation, but for ease of thought, we have states 1, 2, 3. So suppose that customers arrive according to a Poisson process at rate 6 per hour. So there's a lambda 0 equals 6, a lambda 1 equals 6, and a lambda 2 equals 6. And there's nothing here because they don't enter. If there's 1 in service plus 2 waiting, they don't enter. So those are the birth rates up at the top. Now, the tricky part is the death rates, and you have to do a couple of things. You're going to go down with these death rates, but you have service time, mean service time equals 12 minutes, which is 1/5 of an hour. This is per hour. So we keep the units. We're careful, and we use the same units. We use hours throughout or minutes throughout, right? We use the same units. So the mean service time is 12 minutes, 1/5 of an hour, and the mean patience, or the mean time to abandon, we're told, is 15 minutes, which is 1/4 of an hour. Okay, this stuff, one part of the model building up here is we're told the arrival rate is 6, so this is totally clear. But we're not told anything about service rate and abandonment rate. Instead, we're told the service times are IID with this mean. And the times to abandon are IID with this mean. So the rates of these are exponential variables. Service times are assumed to be exponential, and abandon times are assumed to be exponential. So the rate here, the service rate, individual service rate, is 1 over the mean in hours, and 1 over the mean, so we'll call this theta, equals 4. So that if we did this in general, this would be, going down would be the service rate. There's one server, but there's one server here, so it's still mu, because even though there are 2 people there, there's only one server working, but there's an abandonment rate. And then here, there's one guy in service plus 2 waiting, and so there's twice the abandonment rate. And so the rate would be 5 plus 4, 5 plus 8, 13, 9, 5. These would be the rates down here. So this part, part of this is half the problem, right? Half the problem, you've got this barber shop. In this case, there's one barber. There could be 2 barbers, 3 barbers. The customers are impatient, so you've got rates up, rates down. You want to make the model. In this case, this was given to you directly, but you have only one server, so when that server's busy, there's a service rate of mu, and when there's the customers abandon, only from the ones that are waiting, not the ones in service. The one in service is not abandoning. So when there's 2 in the system, there's 1 waiting, so there's 1 theta. When there's 3 in the system, there's 2 waiting, 1 in service, so 2 theta. And then these things, the theta and the mu, are the reciprocals of the given mean. So that's the model. So half of this problem is, there's the barber shop, it's birth, death, and you've got to get the birth rates and the death rates right. So that's part of it. Now you're going to solve it, and solving it is, you could memorize the various levels of the solution, but the balance equations, so we know in some sense that we have this, but we don't want to solve the systems of equations. We're going to have alpha 0, lambda 0 equals alpha 1, mu 1, alpha 1, lambda 1 equals alpha 2, mu 2, alpha 2, lambda 2 equals alpha 3, where these are death rates, these are birth rates. It's the flow. The flow across here, up and down, has got to be equal. So you have these balance equations. And so in our case, we're going to have here, we're going to have alpha 0, 6 alpha 0 equals 5 alpha 1, 6 alpha 1 equals 9 alpha 2, 6 alpha 2 equals 13 alpha 3. And then, of course, we have alpha 0 plus alpha 1 plus alpha 2 plus alpha 3 equals 1. So we have these 4 equations in 4 unknowns, and that's what we'll be solving. So if we do this, we would end up getting alpha 0 equals R0 over R0 plus R1 plus R2 plus R3. This is the solution of this, and this is where R0 is 1, R1 is lambda 0 over mu 1, R2 is equal to lambda 0, lambda 1 over mu 1, mu 2, and R3 is equal to lambda 0, lambda 1. So in this case, we would have 1, and let me just put 1, 5, 6, and then 5/9 times 5, 6 is 25 54ths, and 6 times wait, am I doing something strange here? Is this actually that hard? Maybe. Looks just to see. Yeah, that's okay. But then here, so let's say this is 5, 6 times lambda. Wait, I've got this backwards. 6/5. And 6/5 times 6/9. But that's 2/3. So it's 12/15. And this is 12/15 times 6/13. And this is 2, 5. So that's 24/65. 65. Okay, so to get all this, you get you then think of all this thing, you put them all over you have the thing being 60, you have 65, multiply by 65, and you get 13 times 78. That's 12/15. I could be reducing that as 4/5. So if I multiply by 65, I'm multiplying by 13, you get 52. And then 24 over the sum of these, and 130, 143, 193, 195, 219. So okay, so this would be alpha 0, alpha 1, alpha 2. Okay. I mean, you proceed. Anyway, that you've got there. You were doing that to find that. So then, now you've got these, and actually, so there's maybe 3 parts of this problem. First is the model, second is finding this, and third is answering the other questions. And if you answer the other questions, it ought to be sufficient to give your answer in terms of the alphas. And so you might have done this wrong, but you still get the right answer if you now give the rest of the answers in terms of this. So there's 3 parts, right? The model right, the calculation of the steady state distribution right, and then questions with it. And you should be getting. So if we address those questions now, we can do it in terms of the alphas and think of it a little bit in terms of these. Okay, so let's look at the questions. B, what is the long-run proportion of time that the barber shop is empty? There's nobody being served. B. Okay. At what rate are customers served? What is the departure rate of served customers? So the departure rate, departures can occur. The departure rate is the probability that the server is busy times the service rate, which in this case is, I guess, 5. So this is not the death rate in all the states. This is the constant service rate, which is here is this mu. This mu is the service rate. This is mu1, mu2, mu3. Right, the death rates. It's the service rate here, not the abandonment rate, because this is departure rate of served, not abandoned. So we're finding the probability the server is busy and multiplying by the service rate. That's the rate at which customers are coming out, being served, having been served. Okay. What is the long-run proportion of arrivals that abandon? We can find, now we want proportion that abandon. And that's abandonment rate divided by arrival rate. Right? And then arrival rate is just 6, is the lambda. No matter what, the arrival rate is 6. So potential customers are coming in at 6. That means proportion of potential customers that abandon. So, I don't know, maybe it's ambiguous. Is it clear? What is the long-run proportion of arrivals that abandon? So it's the proportion of customers that enter the shop, wait, then abandon before starting service. So the abandonment rate is alpha 2 times theta plus alpha 3 times 2 theta, right? Because this is the probability there's 2 people there and 1 is abandoning at rate theta. This is the probability 3 people are there and 2 of them are abandoning at rate 2 theta. So this would be, you'd get the 78, 52 over 219. The abandonment rate is 4 plus 24 over 219 times 8 would be this part. And then we divide by 6. Okay? I mean, that's sort of, are there any issues? So, I mean, the thought, let's just think here. One issue, just to review this problem, one issue is you've got birth-death process. Birth-death process is continuous time Markov chain, but you always go up 1 or down 1. So when you go up 1 and down 1, you don't have to solve this. So when you have 4 states, you don't want to solve a system of 4 linear equations, right? You don't want to do that. Instead, you can do the birth-death thing, and it's recursive, so you can write the answer down. So then you need the birth rates and the death rates. So then, and the trickiest part in the model is to get these death rates right when you're given the information in a different form. But having gotten that, you then solve the balance equations to produce the steady-state distribution. And then with the steady-state distribution, you answer these related questions. And this is sort of, if you understand this problem, as you sit there and look at it, you probably got it to do any related thing. Okay? Hopefully, well, hope. On the other hand, hopefully, the right reaction is, yeah, it seems clear. Hopefully, you don't feel, gee, we could have done this whole course in one class, and why did it take us all year to do it, or whatever, all term. Okay, so anyway, let's leave this. On the other hand, hopefully, it's making sense as I'm going through it. That's the right reaction, is that it makes sense. Okay, now we're coming to the third problem. Loser enterprises. It says stock. Sounds like something you'd want to buy, right? Loser enterprises. Okay, suppose that you own stock in a company, Loser Enterprises, whose current price is $50 per share. Suppose that changes in the stock with time measured in months occur according to a standard Brownian motion. Okay, so the stock price. The stock price here is this in the model, where this is standard Brownian motion, which means zero drift and unit variance coefficient. So that's the price as a function of time. What is the expected stock price at the end of 12 years, 144 months? So this is true price for T in months. Time is measured in months. That's the question is saying, time measured in months. So what is the expected stock price at 12 years, which is 144 months? So you want this. You want T to be 144 months. 12 years is 144 months. But that's 50 plus B of 144 with the expectation here. But the expectation of standard Brownian motion is 0, so this is just 50. No problem. what is the probability that the stock price at that time, after 144 months, is greater than 62? So we want the probability that X144 is greater than, was it 62? Greater than 62. So this time. Okay, so we just put that, what we had there, that was 50 plus B of 144 greater than or equal to 62. We subtract 50 from both sides, and we get probability B144 greater than or equal to 12. We note that this is normal, mean zero, variance t, so 144. But if this is the variance, that's the same thing as 12 normal 0, 1 greater than or equal to 12. Because this, if we take this variance and move it in the front, the square root, if this is 12, the variance of this is 12 squared times 1. So this is the same. And then that's the probability that normal 0, 1 is greater than or equal to 1, which is 1 minus, where phi of 1 is the standard normal CDF that you look up on page 81. Which is, in my view, that's actually the more relevant thing to remember, right? I mean, rather than remembering the elements of the table as you just know where the table is, right? But you have the table with you, right? It's good to know that this too, maybe. This thing is something like this, but I guess. Okay. Give an expression for the probability that the stock price goes above 74 at some time during the 144 years. So now we're being asked the probability that the maximum of x of s, 0 of t, say, x of t 0 less than t less than 144 greater than 74. The maximum. Now we want to know if the price ever goes above 74. We change this to the probability of the max of 50 plus b of t greater than 74. And then we subtract 50 from both sides inside there, right? So we're ending up with the probability that the max of Brownian motion, 0 less than t less than 144, let's see, I've got to be here, greater than or equal to 24. Okay, so this is one of the things that you should know from Chapter 10. In some sense, you've seen more than you're being held accountable for, which means it's your own. This part is something you're supposed to know, but I'm not assuming you know geometric Brownian motion, or we're evaluating options, so forth. The idea is that the motivation of making millions will be sufficient for you to learn that stuff, and that this will be just a sample. So this is kind of, but in this case, we have the reflection principle. So we're thinking, here we are, standard Brownian motion. We want to know if we ever get over here. We know the probability of ever hitting here is twice the probability of being up here at the end, because if we do hit, half the time we stay up, and the other half we end up down here. So this is equal to twice the probability that B144 is greater than or equal to 24, which is twice the probability that normal 0, 144 greater than or equal to 24, which is twice the probability that 12 normal 0, 1 greater than or equal to 24, which is twice the probability normal 0, 1 greater than or equal to 2, which is approximately twice, 2 times 0.023, about 0.046. But so the key point is this reflection principle that tells you that the probability that the maximum is bigger than something is twice the probability that the process itself at the final point is bigger than that. So we're using this property of the maximum, which is this reflection principle. It's saying that this path that ends up here has a corresponding path that ends down here. So hitting this level is half the probability of ending above here. In doing this reflection, we used very strongly that the process is just standard Brownian motion. The Brownian motion has no drift. If it had some drift, the thing would be different and more complicated. Okay. What is the expected conditional price after 4 years, given that the stock is 14 after 12 years? So let me just draw this picture. Here's 12 years, 144 months. And here we start at 50, and you're told here that it's 14 things. Loser Enterprise is living up to its name. And then you're asking about 4 years, which is this, and you know you're here at the end. And you want to know given that you started at 50 and given that you ended up at 14, where are you here? And the formulas in the book, also in the early sections 1 and 2, about the conditional distribution of Brownian motion in the middle. And that's again normal with a specified mean and variance, which the formula is there. And the mean lies on this line. So then you're here. And so you went down 36. And this is 1/3 the distance, so you've gone down minus 12. So this point is 38. Right? Because it's going to be on this line. But the formula is sitting there. The formula for the mean and variance of conditional Brownian motions in the book on the page there. So you think, well, okay, I can look it up. The mean is going to be on this line, and the variance is going to have this distance and this be proportional to these distances divided by the length. So they make sense. The formulas are there, but they also make sense, that's good to look at. Okay, then what is the conditional probability that the stock price after 4 years exceeds 50, given that it's here? So you want to know what's the probability that you're up above here. Well, the mean is here, so you're going to have this distribution here is going to be the probability that x of 4 years greater than 50, given x of 12 years equals 14, is going to be a probability of a normal m sigma squared greater than x. In other words, this conditional distribution here is normal with this mean and a variance, and you can calculate. So then you've got something like this, right? So you've got the normal thing, so then you rewrite it as normal 0, 1 greater than or equal to x. You subtract mean from both sides and divide by the standard deviation, and you get this. So the standard normal approximation. In other words, I'm not doing all the calculation of the variance, but you want the distribution of being up here. And the facts are that the conditional distribution is again normal with this mean and a variance you can calculate, which means the problem reduces to the probability that a normal distribution with a specified mean and variance are bigger than some amount. You subtract the mean from both sides, you divide by the standard deviation from both sides, you get standard normal. You look this up in the table. Not totally happy. So the normal approximation should be, in various cases, you could be using that to know the Poisson, to know compound Poisson, and to work with Brownian motion. You might get normal distribution. So you want to know this. I mean, this let me just echo this, because we've done it several times. But so if we wanted this, but remember that this if it's got mean m and variance sigma squared, it's just m plus sigma times the standard normal. So this is what this is. So then if you rewrite that, now it's clear. Now it's totally clear what to do. Subtract m from both sides and divide by sigma from both sides. X, subtract m from both sides, divide from sigma both sides, right? That's this, right? So somehow or other, problems are going to reduce to the distribution in question is approximately or exactly normal with some mean and variance. You want to do this to reduce it to standard normal, which is the table in page 81. So then one question in the part is, what are these mean and variances, which is the previous part of this problem, the formulas for this conditional thing. The fact in Chapter 10 is this conditional distribution, given the values here and here, given that it's Brownian motion, this conditional distribution is normal with a particular mean and variance, which means you get this formula for the appropriate mean and variance, and you do this. Okay. Launching satellites and new cars. Let us do these in reverse order. That I don't want to miss new cars, because that's important, and you've had satellites already. Less important, although maybe I should be trying hard to make sure that you learn satellites, that you become experts in satellites, especially if they really do, if they do develop a satellite launch site from Manhattanville. Columbia does that, and you might be called upon to work on this project. It could be nice if you could start a rumor that C's professor proposes launching satellites from Manhattanville, and we could have protests on campus about we could stop this before it gets too far. Okay, well, anyway. Okay, so let's consider Elizabeth's new car. Elizabeth's new car first, and then we'll come back to the satellites, irresistible as they are. We'll come back to them. Okay. Elizabeth buys a new car as soon as her old car breaks down or reaches the age of 8 years, whichever occurs first. A new car costs $20,000, but there's an additional cost of $4,000 whenever the car breaks down. Right? It's not good to have the thing break down. Okay, there you can think of a whole lot of stories, right? Suppose that an 8-year-old car has a resale value of $5,000. Now, this is set up to be an optimization problem where you would actually, in such a situation, figure out when you should replace the car, which is kind of like a realistic problem in cars and trucks and subways and so forth, where as it's getting older, it may be worthwhile to replace it before it gets any older, because it's incurring cost being older. It may actually make it not so good. So this is a simple version of that problem. But what we're assuming happens here is Elizabeth buys a car, it ages some amount, and it either fails or doesn't fail by 8 years. If it doesn't fail before then, she gets a new one, and it starts over again, right? So the story is you have time, and here we buy a car, and then there's some time which could be, so let's say 8, this is 8 here. So maybe the car lasts, it gets to here. The next car lasts, it gets to here. But the next one breaks down here. So at that point, she buys another one. And then that one lasts 8 more. And so what you're seeing is a renewal process. Things are starting over with each new car. So the key thing to think about here is that at the time each new car, whether it's a breakdown, there's no breakdown, no breakdown, breakdown. No breakdown, maybe another breakdown. So there either is no breakdown and 8 years goes by, another no breakdown, 8 years goes by, but a breakdown. But at each of these times, she buys a new car. So what do we want to do here? Well, what is the expected interval between the times that Elizabeth gets a new car? What is Elizabeth's long-run average cost for car ownership? And in the long run, what proportion of Elizabeth's cars break down? So if we think about the long-run cost, or any of these things, the long-run cost is, that we're looking for, is the expected cost per cycle, which is car, expected length of cycle. So that's that car ownership period. Okay, so we're thinking about this. This interval is going to be something less than 8, right? It's going to be 8 years, but if the car breaks down, it's going to be something less. Okay. Suppose that the lifetime of each car is uniformly distributed between 2 years and 12 years. So, this is rather unrealistic, I guess. 2 and 12 or 4, 7, 8. So this is the distribution. This is the density function. So this is 10. This is 1/10. This is f of x. The PDF, the density function of the lifetime of the car. But what's going to happen is, if this region, it's going to, if the lifetime is between 2 and 8, the car is going to break down. If the lifetime is greater than 8, at that age, she's going to replace it. So this isn't going to happen. So what we want to do is, we're going to get, what is the expected lifetime? Well, the expected length, called t is this length, is from 1/10 is the PDF. If we wrote f of x dx x from 2 to 8 plus 8 times, this part we could be doing 8 to 12 f of x dx, right? We would have integrate between 2 and 8 this expected value formula, and then we're just going to get a lump length 8 if it's between 12 and 8. So we would have the expected value of t is between 2 and 8, 1/10 x dx plus 8 times 1/10 between 8 and 12. So this is plus 4/10 times 8 is 3.2 for this chunk there. And here we have x squared over 20 between 2 and 8. So we have 64 twentieths minus 4 twentieths equals 60 twentieths equals 3. So we have 3 plus 3.2 equals 6.2. But this is probably the hard part, right, of this problem. I mean, part of this problem is to remember that you have this renewal structure. So chapter 7 is you start over with every car. So what you want to do is do stuff with this expected length of the cycle. And this theory is this kind of thing, which is part B. But you want to compute the expected length of the cycle. You know that the cycle is, this distribution is going from 2 and 12, but it's going to end at 8. So you're actually computing the expected random value, which is this. This is the PDF, and this is the x, f of x times x. You integrate the PDF over this portion, but you just multiply by 8 if it's bigger than 8. Because your answer is going to be, the length is going to be 8 if it's bigger than 8. And then this is the PDF, because the PDF is uniform over between 2 and 12, so it's 1/10. So this PDF is 1/10 here, and you're just using this is the standard. Well, so it's not a standard. You're not writing down just this. You actually have to think a little bit, because it's a density below 8 and it's not a density above 8. So it doesn't quite just slap in the formula. You have to think a little bit, right? You have to say, oh, this is true up to 8, but not after 8. And that's where you get, this is the standard formula, but afterwards we just get this 8 times the probability of being there. And the answer is 6.2. You certainly better not get an answer bigger than 8. Right? Okay, that's, a sign of, it's that the length of, they're going to, that some cars are going to last to 8 and be replaced, and others are going to fail. Okay, so 6.2 is this part of this part, expected length of the cycle. Okay, now, what is the long-run average cost for car ownership? So then we want the cost in these cases. We want the expected cost per cycle. So what have we done here? So if we go back here, we're actually having this. So if we do this probability, we see this is 4/10. So we have 4/10 is that so maybe the point is replace, break down, replace old. So the replacing the old does not break down, This occurs with 0.4 and this occurs with 0.6. Because here's it does not break down if it's between 8 and 12, which is 4/10. And the rest it does break down. Okay, now, let's see what happens. So what I'm trying to do is find the expected cost per cycle, and I don't really need to know when the car breaks down, if it breaks down, for this part of the problem. I need to know that for what we just did, the expected length of the cycle. So what am I, a new car costs $20K, so let's put this stuff down here. What's the cost? The cost per cycle. The expected cost per cycle, no matter what, it's $20K. Additional $4K is occurred whenever a car breaks down, plus 4K times 0.6. This is the probability of breakdown. Plus minus. We get a resale value if it's 5, if it lasts. So if it doesn't break down, we're going to have a minus 5K times 0.4 in terms of cost, because we actually get this back. We get 5K back for our used car if it does not break down. A new car always costs $20K. There's an additional cost of 4K whenever a car breaks down. An 8-year-old car has a resale value of 5K, so when it's still working, you just sell the 8 car and you get 5K back. So in terms of cost, you have 20K every cycle, 4K with probability 0.6, and minus 5K with probability 0.4. So you get 20 plus 2.4 minus 2.0 equals 20.4. So you get, your long-run cost is 20.4 over 6.2. The expected cost per cycle divided by the expected length of the cycle. This example is a prototype of that whole chapter, that renewal theory, right? This sort of, and this problem is in there. It's that things start over and you find the expected cost per cycle and the expected length of the cycle. You can represent all these problems in that way. And so you can, the inspection paradox or other problems that look more complicated. But though this problem is a little bit illustrative of that the idea, I would say that the high-level idea of the problem is actually simple, and that if you try to memorize too much, it won't work. In other words, you might want to memorize expected. In other words, I had to think to do these two things rather than just crank out some formula. I mean, the fact that this is the formula I memorize. This is the level at which you should memorize the expected cost per cycle, expected length of the cycle. I memorize that. Then I have to calculate these. I actually have to think. I mean, I'm not using just the expected value formula with these things. Quite, right? It's easier to think this than it is to chug it into some formula. The point I'm trying to make is these things are easier to do thinking a little bit than they don't fit the formula. In other words, this thing turned out to be not just this. You know, if you think it's got to be this, or it's not, not the discrete version, or the continuous version, this thing wasn't either of those. And this, which involved some density, this didn't involve any density. Because you could just figure this part out and fill it in. I'm just saying a little bit of thinking. If you just think, oh, this is always there, when it breaks down, what's the probability of these things? You've already found these in the previous part of the problem, if you just think about it. So I think there's a moral here that the main story is simple. And then the details, actually, in many cases, the details follow from thinking rather than memorizing. Right? I mean, if you think that it all plugs into a formula, it isn't there. Right? It just isn't there. This is kind of consistent where half the problem is that there's some framework that works. And then part of the problem is that you should understand what's required and just put reason and think a little bit rather than memorize everything. Right? I mean, this is just a high level view. I'm trying to, I think that's the right thought. So part of the problem comes when you try to memorize too much. Right? You try to anticipate in detail the whole problem, and the next problem won't be exactly like that. There's only part of it you want to memorize. And the part of it's actually easy. Once you realize what to memorize, it doesn't require too much. This part goes a very, very long ways, and it's very simple. And then when you think about this, it's actually good to just think it through rather than have it try to memorize what it is exactly. But there is an element here where you're left with the hard part of the problem is some sort of basic probability where you're writing expected value down of something, right? And that's actually harder than the stuff in the book, the main content of the book. Okay, well, okay, let's talk about the satellites. So the satellites, I think, is closely related to what was on the exam. So let's finish with the satellites. Okay, satellites. Suppose at time t, satellites are launched in space according to a Poisson process with rate 2. Suppose that each satellite spends a random time in space before falling to the ground. Suppose that these times are independent and identically distributed with a cumulative distribution function having mean 18 years and, let's see, that's a strangeness. EX equals 10. Looks very odd. Wait a second. Sounds like it's doubly, okay, let me see. Seems that's inconsistent. Satellites are launched into space according to a Poisson process, 2 per year. They spend a random time in space, x. Looks like 10 and 18 both. Somebody must have said, what's going on here? And we must have said, oh, it's one of these. Let's suppose it's 18. It looks like that point is this and this don't go together. We need one of those, but not both, right? This doesn't look like that's okay.
The time is
Am I miss?
the time spent in space is a function of x.
Let's see. Suppose we're starting in the saddle launching the speed.
And 18 is the mean of CDF. And 10 is
No, x has to be the same. They're the same thing. So the mean of the CDF, the g of t is the probability of x less than or equal to t. So the mean of g is the mean of x. That's, I mean, when you talk about a random variable, it's got a mean, and the CDF's got a mean, and they're the same thing. That's so these things can't be different. That's, I mean, there isn't any. The person who made this exam should be executed. Just, there's no excuse. Okay, it's inconsistent. So we'll take one of those numbers. So in the long run, what happens in the long run? So when this problem is this, the infinite server queue. So this is also infinite server queue with Poisson arrivals. So this is sitting in chapter 5 with the Poisson. So the infinite server queue, and there's an arrival rate, and there's a mean, and let's say this is whatever, 18, and this is 2 per year, and this is so many years. So the long run, the expected number there in the steady state is lambda times Ex is equal to 2 times 18, assuming that the mean is 18 and not 10. Maybe charitably, maybe the last 0 is supposed to be an 8. The typo. Anyways, there's only 2 different specifications, not 3, so that helps. Okay, if this process continues a long time, what's the approximate probability that there are more than 48 satellites in space at any time? So you're thinking, well, it's probability at some time, this is in steady state, there's greater than 48. And once again, we have normal approximation. It's exactly, you could write this down as Poissons, so it would be, it has Poisson with this 36, so it would be e to the minus 36, 36 to the k factorial, k equals 48, greater than or equal to 48 would be this, right? That would be the exact probability. That's not what's wanted. This is not what you'd want to compute. But you'd want to recognize that a Poisson random variable with a mean 36 is approximately normal. So the mean and the variance of a Poisson distribution are equal. So this is approximately, this Q infinity is approximately normal mean 36 and variance 36. Because it's exactly Poisson, it has the same variance as mean. And then you're asking, so instead of this, you're asking the probability that this is approximately normal 36, variance 36, greater than or equal to 48. And then we repeat the thing about subtracting the mean and dividing by the standard deviation. So if we do that again, well, first of all, that's 36 plus normal 0, 36 times normal 0, 1, greater than or equal to 48. Probability normal 0, 1, greater than or equal to 2. right? So we've represented as the mean outside multiplied by the standard deviation. So we subtract the mean from both sides, divide by the standard deviation. We have this. So that that's there repeatedly in every problem is because the normal approximation is the way to quickly see what these probabilities are in almost all these situations when the numbers are large. Okay. Now you get this weirdness. Give an expression for the probability that none of the satellites in space at time t was launched before s. Okay. So you now want this picture. You're thinking at t, and then you have s, and you want to know what's happened. So you're thinking their satellites are being launched at these random times, Poisson process, and they have times that they spend in space, random times. And you draw this picture. And what you're looking for is, repeat, none of the satellites in space at time, give an expression that none of the satellites in space at time t was launched before s. So the satellites in space at time t that were launched before time s is this region, right? And so every region here has a Poisson distribution with a mean equal to the integral of the intensity over this region. So this is a Poisson random variable with a mean we've got to calculate, and we want to know that this probability of this random variable is 0. Right? So the probability that a Poisson random variable, let's call it n, probability n equals 0 is just e to the minus m, because we've got m to the 0 and 0 factorial. That's 1. So we just want e to the minus m. So our problem is to calculate the m for this region. And then we have this, we have a lambda going here, so there's a lambda u. And then up here, if this, well, let's see, so if we make this u, this is t minus u, this is t minus u. So this is then lambda u g 1 minus the CDF g of t minus u du, and that's going to go from s back. So you're looking here, you're saying u is this distance, or this is u is measured this way. U is measured this way. This is t minus u. So lambda u is the intensity here, starting, say, at 0. Lambda, this is u. This is t minus u. So u is lambda u. And then this height is t minus u. So the service time should be greater than t minus u. So this is the intensity at u of the arrivals. And this is the probability the service is greater than t minus u. And then you integrate this region from 0 to s. So that's finding this m. So this is this m, which is the rate that goes with this picture. So the main thing here is that this picture has that there are arrivals according to a Poisson process, and they spend a random time in space. And so the regions in here tell you where the satellites are. In other words, the satellites that are present at time t are the ones that our service times are greater than such that they wouldn't have left by now. So the ones down here that are below this line have left by time t, and the ones are still there. And that everything in sight is Poisson. So the fact that everything in sight is Poisson meant we did a normal approximation before, and here you're going to just find the mean of that Poisson thing. In the final part, you're supposing g is exponential. So you've got some. Let's see. So what are we told in this final part? 20 side. You're told. Here you are. Here's t. Here's s, and you're told that there's actually. So here, there's actually 20 here at this time. There's 20 here. Let's put 20. and you want to know what's happening at t. So what you think about here is you know that these are here, and then there's going to be some new arrivals. So the ones that are there, each one that's here is going to have an exponential time there because they're assumed to be exponential by the lack of memory. They're going to each be here. E to the minus lambda t minus s is the probability that any one of these is going to be here. The expected number, this is there, the expected number of those at s that are there are 20 here. Each one is there at time t with this probability. Exponential, lack of memory, probability that it's greater than this. And then you would have new ones coming from 0 to t. And there would be plus the arrivals from, if you want to make s to t, then g complement t minus u du. And this also would be e to the, this is say mu. If I have this is the rate of the exponential. And this is the arrival rate. So this is this thing plugged in here. So what's going on here is if you're told the number here, then you know there are 20, and they're all exponential, and they actually have the stationary, they're independent exponentials. And therefore, you can then compute their expected values separately. So that's, I guess, that's pretty complicated. But you would know, you could treat the 20 one way, and you could treat the remaining the other way. So you might glass over on the satellites slightly. Actually, the satellites are unlikely, given that you've been abused by satellites on the second midterm already is less likely. However, new cars, stocks, such like the others are more typical. So so the satellites are less likely, and to emphasize again, the options and the geometric Brownian motion and black shoals is not really covered, right? The stuff that's section 10.3 and 10.4 is not covered. So what's covered is illustrated pretty reasonably by the exam, by this exam, and also by the homework. And the exam will be like this. Are there anybody want to make a clarifying question or something? Are there any things to further to discuss? So otherwise, have a productive week, which whatever that means, including hopefully some review of this, along with whatever else you have to do. Yeah, let's see. So this is okay. I'm